microcomputer-based monitoring and control system, centralized intelligence for measurement, proving, and validation, distributed control through modular microcomputers. The turbine fiscal metering system is governed by a network of dedicated microcomputers, each assigned a distinct role: stream monitoring, station aggregation, and prover automation. These processors reside in the central control room, CCR, local control room, LCR, or nearby equipment shelter, and serve as the digital core of the metering infrastructure. Their design is modular to ensure that individual failures do not compromise overall system performance. Each stream typically has its own microcomputer to handle pulse counting, flow calculations, and local diagnostics. A central station microcomputer aggregates all stream data, interfaces with operator terminals, and communicates with the supervisory control systems, e.g., SCADA DCS. The prover microcomputer manages all proving cycles, K-factor computation, and sequencing. While combining these functions into fewer devices may be considered for efficiency, it is only acceptable if availability, redundancy, and regulatory requirements remain fully satisfied. Meter run selection, flow distribution, and calibration launch. From the control room interface, operators can select which meter runs are active, balance flow among streams, and initiate proving sequences. Control commands are transmitted digitally to modulate valves, switch instrumentation, and allocate sampling functions. These controls include critical inputs for real-time measurement of pressure, temperature, density, cumulative volume, and water content. The system maintains a transparent digital footprint for each command and response to support operational audits, redundancy strategy, and fault recovery. Metering systems designed with parallel runs eliminate the need for redundant stream microcomputers. Stream failures are handled by deactivating the faulted run and enabling a standby. In the event of stream computer failure, the affected microcomputer must be hot swappable using plug-in spare units. This approach ensures rapid recovery and avoids production interruption. Each microcomputer is required to preserve essential data during swaps, including meter totals and configuration parameters, digital protocols, and data integrity. To eliminate conversion errors and maintain signal fidelity, digital communication protocols such as HART or Foundation Field Bus are preferred for transmitter to microcomputer links. These protocols support high-resolution signal transmission, device diagnostics, and live status reporting. All analog to digital conversions must meet an overall uncertainty threshold of less than 0.020%. Computation and digital output uncertainty must not exceed 0.001%, ensuring that the metering logic maintains high precision from signal acquisition through final calculation. Environmental hardening and electromagnetic compatibility. The microcomputer system must be installed in an electromagnetically protected enclosure and comply with EMC guidelines. Equipment must be immune to disturbances from mobile radios, power switching equipment, nearby lightning strikes, and parallel power cabling. Protective design includes shielded wiring, grounding isolation, and physical separation of high and low voltage circuits. The system must also be secured against physical and cyber tampering through locked panels, password protections, and encrypted interfaces. Power supply continuity and data retention. The entire microcomputer system must be supported by an uninterruptible power supply, UPS, with at least 30 minutes of autonomy. During power loss, volatile memory data, including flow totals and system configuration, must be retained for a minimum of 31 days. Following extended outages, the system must resume operations automatically without manual reboot. Any loss of UPS power must trigger an alarm and activate internal backup systems to prevent data corruption. Event logging, alarm management, and security access. All operator entries, alarm acknowledgements, configuration changes, and proving initiations must be logged in a secure event log. Each entry must include a timestamp and user identification to ensure full traceability. Configuration changes, such as downloading a new meter factor, must preserve the previous value in memory for audit comparison. The user interface must feature access control layers to restrict critical functions to authorized personnel only. Security mechanisms may include key switches, login credentials, and multi-factor authentication, depending on regulatory requirements. System interfaces and integration with SCADA DCS. If integration with a plant-wide SCADA or DCS system is required, the microcomputer architecture must support standardized serial communication or digital data bus protocols. Interface development must be coordinated with the DCS SCADA vendor to ensure compatibility in polling rates, signal conditioning, and alarm formatting. The system must allow both real-time data transfer and periodic reporting, e.g., hourly, daily totals. All critical data must be displayed on operator consoles with intuitive visualization, including valve status, flow rates, alarms, and station diagnostics. Error detection and safe fail behavior. To minimize the risk of undetected faults, the system must validate all analog signals against preset alarm thresholds, slightly above and below nominal zero, and full-scale values. This prevents false readings due to cable faults, transmitter errors, or signal drift. Any unexpected value outside these bounds must trigger an alarm and initiate fault containment protocols. Additionally, if flow is detected on a non-selected meter run, the system must automatically stop counting and alarm the anomaly. Operational continuity and measurement transparency. The microcomputer-based system is the operational anchor of the Fiscal metering package. It guarantees synchronized control, high-precision computation, and secure data logging. When designed with failover logic, memory preservation, secure operator access, and protocol-based communication, it ensures not only regulatory compliance but also measurement transparency in all operating states, from normal flow to calibration, proving, and recovery. Utility provisioning and infrastructure resilience. Electrical power architecture for system continuity. The turbine Fiscal metering system is categorized as a vital service load, demanding robust and redundant electrical infrastructure. Its continuous, failure-free operation is critical for custody transfer accuracy, contractual reporting, and regulatory compliance. To meet this, the power supply must include full duplication from the energy source through to the field instrumentation. This architecture eliminates single points of failure and supports uninterrupted flow measurement across normal, degraded, and recovery scenarios. Primary and UPS supply design. The system shall be powered from a 400 240V VAC, 50 Hz 3-phase and neutral supply, as defined by the site standard. In addition to the main supply, an uninterruptible power supply UPS must be provided capable of maintaining system operation for a minimum of 30 minutes. During this window, the metering system must retain volatile memory data, such as integrated totals, configuration parameters, and system states, to avoid data loss and enable seamless recovery. If the UPS autonomy is exceeded, the system must still retain all critical records through embedded non-volatile memory or a local backup. A separate non-vital 400 flastage and a 240 VAC feed should be supplied for auxiliary loads such as local lighting or non-essential electronics. This division preserves primary metering integrity during partial shutdown or emergency load shedding. Grounding and neutral configuration. For both single-phase and three-phase UPS systems, the neutral must be solidly earthed to ensure a stable reference and minimize transient faults. Grounding integrity is essential for both equipment protection and signal stability, particularly where long analog signal lines or digital communication links are involved. All grounding connections must comply with site standards for low impedance and corrosion resistance. Air supply for pneumatic actuators. Where flow control or valve actuation is pneumatically operated, instrument air must be provided to the skid. The air supply must be clean, dry, and oil-free, as contamination will degrade actuator performance and increase failure risk. The air pressure specification must be clearly defined in the requisition. Connections must terminate in half-inch NPT female threads, and all pneumatic tubing and fittings must be constructed from AISI 316L stainless steel. For sour service environments, materials such as Monel or Hastelloy C may be specified. Copper tubing is explicitly prohibited due to corrosion and safety risks. Material selection for utility lines. Utility interfaces must be designed for compatibility with hydrocarbon service environments. All tubing, cable trays, and junction boxes associated with electrical or pneumatic utilities must meet corrosion and environmental classification standards. Materials must maintain integrity under exposure to temperature extremes, salt-laden air, vibration, and hydrocarbon vapors. Where hydrogen sulfide H2S may be present, material selection must be aligned with NACE or DP recommendations for sour service compatibility. Heat management and equipment ventilation. Enclosures housing power supplies, UPS units, or control electronics must be ventilated or temperature controlled to prevent thermal degradation. If passive cooling is insufficient, forced ventilation or air conditioning must be integrated. All cooling solutions must preserve the certified environmental ratings, IP NEMA, of enclosures and ensure that condensation, dust ingress, or thermal cycling do not impair system function. UPS loading and monitoring. The expected electrical loading of the UPS system must be calculated and provided by the manufacturer in the technical proposal. This includes steady-state loads, peak inrush during startup, and reserve capacity for system expansion. Monitoring systems must include visual and remote indication of UPS status, battery condition, and charge cycles. Alarms for low battery, inverter failure, or load imbalance must be connected to the metering control system and DCS interface. Utility integration as system enabler. The availability, stability, and quality of utility inputs, especially electrical and pneumatic, are foundational to metering system reliability. Without engineered redundancy and protection, even the most precise instruments and advanced control systems cannot deliver the performance required for Fiscal certification. Properly designed utilities transform the metering system from an instrument package into a hardened infrastructure, capable of continuous operation under stress, compliant with safety protocols, and aligned with the operational demands of critical measurement. Technical requirements, field-mounted components, structural, material, and environmental fitness for operational exposure. Skid design for mechanical integrity and access. The metering skid must be designed as a self-supporting, all-welded steel structure that ensures mechanical rigidity under operating and lifting conditions. The layout must conform to project dimensional constraints while optimizing access to all mounted instruments, valves, and components for inspection, maintenance, and calibration. Offshore installations require particular emphasis on weight minimization with clearly identified center of gravity and lifting points engineered to prevent deformation during handling. A full coverage drip pan must be integrated into the skid base, sloped to drain toward a single collection point. This drain must terminate in a flange connection suitable for integration with the facility's hazardous drainage system. Vents and drains must be provided at all piping high and low points with visual indicators on each drain to confirm fluid discharge. The structure must retain full integrity independently of the process or measurement equipment mounted to it. Just material compliance with process compatibility. All piping and valve materials must be selected based on compatibility with the specified process conditions: pressure, temperature, chemical composition, and cleanliness. Wetted components such as turbine meters, strainers, and instrumentation must be constructed from materials that prevent corrosion, erosion, and stress cracking under long-term exposure. In hydrogen sulfide or other corrosive services, specialized alloys such as stainless steel, Monel, or Hastalloy may be required. Thermal relief valves must be installed on any liquid-filled sections where thermal expansion could cause overpressure, especially in systems with block valves or closed ends. These relief devices must discharge to a safe collection system. During factory testing or site commissioning, turbine meters must be replaced with spool pieces manufactured to the same specifications as the skid piping and supplied with matching flanges and gaskets. All headers and branch lines must include mechanical flexibility to absorb expansion differentials, especially when some meter runs are offline. Instrumentation compliance for hazardous and outdoor conditions. All field instruments intended for installation in hazardous areas must carry valid certification from a recognized testing authority. Protection methods such as intrinsic safety, explosion-proof enclosures, or increased safety designs must be compatible with the project's electrical classification zones, gas groupings, and temperature classes. Instruments must be capable of operating reliably under outdoor environmental exposure, including solar radiation, humidity extremes, and airborne contaminants. Field instruments must be rated for ambient temperatures ranging from 65 degrees Celsius to plus 55 degrees Celsius, with resistance to condensation, precipitation, ice formation, and wind speeds up to 30 meters per second. They must also withstand high humidity levels up to 100%, salt spray in coastal locations, and airborne chemicals such as hydrogen sulfide or ammonia. Housings must be weatherproof, corrosion resistant, and sealed to prevent ingress of dust or water. Stainless steel, minimum 3/6 is required for all junction boxes, mounting hardware, and cable trays. Electrical cabling, segregation, and grounding practices. The manufacturer is responsible for all cabling within the metering skid and equipment panel, including proper routing, protection, and termination. Cables leaving the skid to interface with plant-wide systems must be specified by the manufacturer for supply by the site contractor. Signal types, including analog, digital, and power, must be physically segregated to prevent interference and ensure system performance. All electrical components must be grounded using a low impedance path that connects all enclosures and devices. Each skid must include at least 2 grounding lugs at opposite corners, with grounding conductors sized for fault current carrying capacity. Instruments and enclosures in areas lacking overhead steel or lightning shielding must include lightning protection systems to prevent surge damage, especially where long signal or power cables are exposed above ground. Field equipment must be laid out to support safe operation and maintenance in all conditions, with all wiring glands, seals, and terminations protected against water ingress, UV degradation, and vibration. Environmental and electrical resilience at the field level is essential to preserve the accuracy, uptime, and safety of the entire fiscal metering system. Instrumentation and electrical, operational resilience, environmental compatibility, and system integration. Hazardous area compliance and certification. All field-mounted electrical and electronic instruments installed in classified areas must be appropriately certified for the designated hazardous zone, gas group, and temperature class. Certification must originate from an internationally recognized authority and reflect the type of protection employed, such as flame-proof enclosures, intrinsic safety, or increased safety techniques. The protection philosophy must align with the overall site safety strategy and be consistent across all installed equipment. No deviation from the specified method of protection is permitted without formal approval. Certification documentation must be available for each component and clearly reference the operating environment for which it is approved. Environmental hardening and climatic durability. Instrumentation and associated enclosures must be designed for long-term operation in harsh outdoor environments. All components must perform within specification across extreme temperature ranges, -65 to plus 55 degrees Celsius, high humidity up to 100%, and exposure to wind-driven rain, sand, salt, and corrosive gases. Instruments must remain functional under icing, frost, and intense solar radiation, with materials selected to resist UV degradation and thermal fatigue. Equipment must be able to withstand pressure variations, condensation cycles, and mechanical shock or vibration. Enclosures must meet ingress protection standards suitable for outdoor industrial environments and be resistant to mold, rodents, and fungal growth where applicable. Material and construction standards. All electrical enclosures, junction boxes, and cable support systems must be constructed of 316L stainless steel to ensure corrosion resistance. This requirement applies universally across installations, including cable trays, instrument stanchions, gland plates, and support brackets. Equipment exposed to the elements must include provisions for drainage, breathers, or purge systems if necessary to prevent internal condensation. Instrument connections must remain sealed against water and dust ingress, using approved cable glands and entry systems. Mechanical robustness must be sufficient to withstand routine operational handling, including calibration and sensor replacement without damage or performance drift. Power and signal cabling architecture. The manufacturer is responsible for all internal cabling within the skid or cabinet, including the routing and connection of all instruments, control devices, and signal conditioning components. External interconnecting cables must be specified in terms of type, length, and installation requirements, but will typically be installed by the site contractor. Cable routing must maintain strict segregation between different voltage and signal classes, such as analog, digital, and power lines, to avoid signal interference and maintain measurement integrity. Cables must be protected from physical damage, ultraviolet exposure, and temperature extremes with proper mechanical support throughout their routing. Grounding and bonding integrity. A continuous grounding network must link all electrical components, metallic enclosures, and instrumentation. Each skid must provide at least two diagonally opposed grounding terminals for connection to the facility grounding grid. The grounding system must be low impedance and able to safely carry fault currents without hazardous voltage rise. Special attention must be given to the grounding of sensitive electronic instruments, especially those with microprocessor-based control or digital signal interfaces. Ground loops must be avoided through the use of isolated signal paths and proper bonding practices. Lightning and surge protection. For outdoor installations not protected by structural shielding or lightning conductors, dedicated surge protection measures must be included. This applies to all signal and power lines that extend beyond the skid boundary, particularly those running in parallel with long metallic paths. Surge arresters, shielded cable, and equipotential bonding must be employed to prevent transient damage from lightning or power switching events. System segregation and diagnostic access. Electrical and instrumentation design must support safe isolation of components for maintenance and testing. Junction boxes must allow individual circuits to be disconnected or tested without disturbing adjacent equipment. Diagnostic indicators, test points, and bypass switches should be included wherever practical to support fault finding and system validation. The field instrumentation and electrical system must be engineered to provide both operational continuity and field serviceability under real-world plant conditions. These systems form the backbone of the metering station's reliability, accuracy, and compliance with custody transfer regulations.